Hello student, good morning. Today we will start Wien bridge oscillator. Previous day we have completed Barkhausen criteria, which is an essential criterion for the oscillation to happen in a circuit. Okay. Now we will study here three different oscillation circuits. First one is Wien bridge oscillator, which we will start. Okay, so let's start Wien bridge oscillator. Wien bridge oscillator. Now why this oscillator is named so Wien bridge? Actually there is a bridge network and this network is first proposed by Wien. Therefore this kind of oscillator is known as Wien bridge oscillator. Okay. Now first of all I am drawing the oscillator, then I will explain all the parts one by one. Okay. First of all, it contains a op amp. Okay, this is your operational amplifier. This is negative terminal and this is positive terminal. And here, now here we have a feedback network, which is our VO. Definitely a positive feedback. You already know that if it is a negative feedback, then this is not an oscillator. And positive feedback, there will be oscillation in the circuit. So feedback path is connected to the positive terminal. Okay. And there are different terms of the different arms of this Wien bridge. And I'm first drawing the circuit, then I am saying here is R1 and R2. This arm is connected here, and from here there is this this kind of connection. Okay. Now this is A node, this is B node, this is C node, and this is your D node, which is connected to ground. Now this is the circuit diagram of a Wien bridge oscillator. Now where is bridge network? This network is your bridge network, and this is called Wien bridge. Okay, so I am drawing this Wien bridge separately. Okay, so how the bridge look like? It has there's actually four arms. That is A, B, C, D. Okay, so I am drawing here. Now let us consider this voltage is your VF. Okay, why VF? Why it is VF? Actually, when we discuss a block diagram of amplifier and feedback ratio, then we have called this feedback ratio as VF. That is why we say it VF. Okay. And this is VO. Okay. Now our bridge network. Here is our VF, and this is your B terminal. What is B terminal? It is your B terminal. Okay, B terminal. So there is R and C and RC series and RC parallel in two sides of B terminal. Okay, so I am drawing this circuit exactly. Here is our CR series, RC series. Okay, and here we have that R1, which is negative feedback, R2, and here we have same RC with parallel combination. Okay, and this is your C, this is B connected to ground, and C terminal, and this is BO, A terminal. Okay, therefore these are the 4 terminals, A, B, C and D, and this is our Wien bridge. That is why this kind of oscillator is known as Wien bridge oscillator. Okay, now first of all let us come to the op-amp part. Okay, which part gives the oscillator some gain. Okay, so I am drawing the op-amp with resistor R1 and R2, and it is used to design a non-inverting amplifier. Okay, so another part is this kind of simple configuration of non-inverting amplifier. This is your input, this R2 to ground, R1, and this is your output. Okay, now which part is that? It is this part of the circuit. You see, I am drawing within dotted part here. Okay, and this is what? This is nothing but a non-inverting amplifier. Why? As signal is given at positive terminal. Okay, now what is a gain? Is a amplifier, then it has a gain. What is A? 1 plus R2 by R1. You already know this kind of equation in your op-amp course. Okay, now the output voltage of the amplifier will be in the same phase with its input. Okay, and also we will set the ratio of this R1 by R2 equal to 2, so that your A, that is gain, becomes 3. Okay, and the choice of these parameters will be apparent soon. Okay, now this is one hand of bridge. Okay, this hand of bridge contains your resistor R1 and R2, but the other arm contains a series RC network and a parallel RC network. I am drawing this part of bridge separately. So how it looks like? It looks like this is your A terminal, R and C, and this is your RC network, then it is to ground, D, and this is your VF. Okay, and this is your V0. Why V0? See, this is V0. V0 is connected with A terminal, and this A terminal is connected with RC series. I am drawing this part of the circuit here. Okay, you clear? First of all, you have this kind of complex network. Now I am breaking this network. First of all, I am saying that this part is your Wien bridge. Next, I have drawn op-amp with 2 resistors, that is right arm of the Wien bridge. Okay, and this gives us some gain A. Why? as this is a op amp amplifier, that is op amp non-inverting amplifier. And second, we have another arm of Wien bridge left, and we draw this arm separately. Okay, this is clear to you, no? Okay. Now we have to study the nature of this network. Actually, this network has a name. It is called lead lag network. Okay, and it will be used as a feedback network to provide the input signal in proper phase to the input terminal of the non-inverting amplifier. Okay, maybe this kind of thing is you cannot understand right away, but if when we calculate all these things, you will understand what I want to say. Okay, now let us characterize this kind of network. Now we have what? We have a C and R, and we have a voltage, and for this network we have an input voltage as VO. Okay, and this is a sinusoidal voltage, therefore it is dependent on some frequency. Now what is the impedance of C? Impedance of C is 1 by j omega C. Okay, as this is your impedance, then at low frequency, that is omega tends to 0, what is the value of impedance? Value of impedance is very high. Therefore we can think that as if there is a open circuited path in case of lower frequency. Therefore lower frequency signal cannot pass through this circuit. Okay, now we start to increase the frequency omega. Okay, and what is happening? As omega is increasing, therefore your impedance is decreasing, and capacitor gradually couples the input signal to the circuit, and we get some output. But when the omega gets much more higher, that is you have 1 by j omega C as your impedance, then this C, that is series capacitor, behave as coupling capacitor, or it will give a short circuit path. But this kind of capacitor also give a short circuit path, so that all the input signal get a shunt path to the ground, so that we will not get any output for very much high frequency. So what we'll get? We will get the output for only mid range of signal. Okay, and that is why this kind of network is also called a band pass filter. Okay, that is it will not pass low frequency and also not pass higher frequency, but it will pass a mid band frequency, and we will call this as a band pass filter. Okay, now regarding the phase of output voltage in this kind of circuit. Okay, now we can recall that whenever a CS circuit is excited by a sine signal and the output is taken across a resistor, we get a lead network, that is output voltage leads in phase. On the other hand, if the output is taken across a capacitor, we get a lag network. Hence our network will have both characteristics, both lead and lag, and therefore it satisfied its name. Okay, and the amount of lead or lag depends upon frequency. Now we therefore expect at some frequency the network will offer zero phase shift. Okay, now let us analyze the network mathematically. Now let us consider for this part, you can see for this part, this series part, my impedance is Z1. Okay, so we are starting mathematical analysis. So what is Z1? Z1 equal R plus 1 by j omega c. Okay, I think you don't have any problem with this statement. Now this is our z1 and let us calculate z2. Okay, now what is z2? Z2 is parallel combination of R and C, that is this part. Okay, this part is your Z2 part. Okay, so what is Z2? Z2 equal, that is 1 by Z2 equal 1 by R plus 1 by R plus 1 by j omega c. Okay, and that implies 1 by Z2 equal 1 by R plus j omega c, and that implies Z2 equal 1 by R plus j omega c whole to the power minus 1. Okay, now what is VF? VF is output voltage in between these two terminals. Now what is VF? VF equal to V0 into Z2 by Z1 plus Z2. Actually, what is the total impedance? For here it is Z1 and from here it is Z2. The total impedance is Z1 plus Z2. Therefore, what is current? VO by, this is the input current, input voltage. Therefore, current is voltage by current, that is Ohm's law, that is VO by Z1 plus Z2. Now what is VF? VF is drop against this impedance, and what is that impedance? That impedance is Z2, therefore I into Z2, and I is VO by Z1 plus Z2, therefore VF become VO into Z2 by Z1 plus Z2. Okay, now what is your feedback ratio? Feedback ratio beta equal VF by VO. Therefore, what is feedback ratio? The ratio which we will get. Okay, now I am saying this part in Bengali so that you can understand in a better way. Okay, দেখ আগের দিন যখন বাকহাউসেন ক্রাইটেরিয়া পড়িয়েছিলাম তখন কি হয়েছিল, আমাদের দেখ একটা গেইন নেটওয়ার্ক ছিল আর একটা কি ছিল, একটা ফিডব্যাক নেটওয়ার্ক ছিল। দেখ ফিডব্যাক নেটওয়ার্কে কি হয়েছিল, আমাদের ভিও থেকে কিছু একটা ইনপুট, একটা কোনো বিটা এরকম একটা ফিডব্যাক রেশিওলা নেটওয়ার্কের মধ্য দিয়ে গিয়ে আমাকে ইনপুটের সাথে কানেক্টেড হয়েছিল। ডেফিনেটলি ফিডব্যাক মানে আউটপুট থেকে ইনপুটে কানেক্টেড হবে, ঠিক আছে। ফিডব্যাক মানে কি, আউটপুট থেকে কোনো একটা কিছু ইনপুটে যাবে, সেটাই আমার ফিডব্যাক। আর সেটা রেশিওটা কত ছিল, বিটা ছিল। বিটাটা মানে কি ছিল, আসছিল V0 আর যাচ্ছে VF, তাহলে রেশিওটা কত, VF বাই V0। ওকে, VF বাই VO। ওকে, তো সেটাই হলো আমার বিটা। সে একই জিনিস কিন্তু আমি এখানেও করছি। ওকে, now I am come back to my analysis. Now beta equal to VF by VO. Now that is equal to 1 by 1 plus, now we have VF by VO. So this is VF by VO, that is Z2 by Z1 plus Z2, and we have the value of Z1 and Z2. Now what is the value of Z2? Z2 is that one, therefore Z2 is 1 by R, 1 by not Z2, Z2 is that one to the power minus 1, so it will occur in the lower side. Okay, by Z1 plus Z2. So but that will have, actually we can simplify this factor by VO whole by 1 plus Z1 by Z2, just divide by Z2. Okay, so this is 1, so only VO by Z1 plus Z2 by Z2, that is Z1 by Z2 plus 1, or 1 plus Z1 by Z2. Okay, now VF by VO, that is 1 by 1 plus Z1 by Z2. So I am writing it as 1 plus first z1. Z1 is that quantity. This quantity is your z1. So 1 plus r plus 1 by j omega c by z2, or 1 into 1 by z2. Z2 is here, therefore 1 by z2 is reverse of that, and here is a minus sign, therefore 1 by r plus j omega c is your 1 by z2. That implies 1 by z2 equal 1 by r plus j omega c. So I am writing here 1 by r plus j omega c. Okay, this is your beta. Now simplify that. So what you will have? 1 plus r into 1 by r, that is 1, plus j omega cr plus 1 by j omega cr plus 1. So 1 by 3 plus j omega cr plus 1 by j omega cr. Okay. Now let us define a quantity as omega 0 equals 1 by cr. So what is our beta? Beta equal 1 by 3 plus j omega by omega 0 minus omega 0 by omega. Omega, now cr means 1 by omega. 1 by cr is omega 0, that implies cr equal omega 1 by omega 0, that implies j omega cr equal j omega by omega 0. So I am writing here. Okay. And similarly for 1 by j omega cr, or 1 by cr equal to omega 0, 1 by cr equal to omega 0. Okay, so similarly we have put these things. Okay, actually we have taken j as common, so let me write another omega cr minus 1 by omega cr. Okay, now therefore this minus sign follows, and here is omega, and 1 by cr equal to omega c. Okay, now if we put with the original frequency f, then what is f?